Hello and welcome. In this video, I will go over some examples of equilibrium of a rigid body. All of the examples are going to be in a 2D dimensional. So the first example asks us to find the support reactions at point A and also draw the free body diagram. Step one is always free body diagram. And you have to figure out what is it that you're drawing the free body diagram for. So I'm going to draw the free body diagram of the beam. That means you're going to isolate the beam and remove any constraints, any support, anything like that, and draw the outline of the beam. So this is a step one of free body diagram. Step two is to put active forces that are trying to mess up the equilibrium. We have a force here and we have another one at 30-degree angle right here, 40 kilonewton. That's the only two I see. Now we have to put reactive forces, the forces that are holding this beam, which is this point A, which is a type of a fixed support. It's either welded or bolted to the wall. So for a fixed support or for any other support, I'm going to create this little table, X, Y, and M. So let's see. This is going to be my positive X, positive Y. It's 100% fixed. So does this move in X direction, right and left? No. Does this move up and down, Y direction? No. Does this rotate about point A? Still no. And I care about those no's, so everywhere you see a no, I'm going to put a force in that direction. So in X direction, I'm going to put an AX. In Y direction, I am going to put an AY. And in rotation, I'm going to put a moment called MA. And this is our free body diagram. So that was a step two of the procedure. Step one of the procedure, excuse me. Step two is to apply equations of equilibrium, which what we have is sigma F and sigma moment about any point is 0, about any point you want. So first let me see how many unknowns do I have here. Unknowns, I have AX, AY, and MA. So these are my three unknowns, and I think I can get three equations. So I need at least three equations. So let me start by sigma forces in X direction being 0. I'm taking this way to be positive. So I start from one corner, kind of make my way, and any force that I see in X direction, I'm going to write it down. The first thing I see is AX, and it's positive. Keep moving. I don't see anything else all the way to the end. So this is going to be 4 cosine 30, and that's in X direction, and that is also positive. So 4 cosine 30, nothing else, so that should equal to 0. This will give me AX of minus 3.46 kilonewton. So the AX or X component of the support reaction is 3.46 kilonewton. This minus means it should have been drawn the other way. But you do not need to go back and change your free body diagram. Your free body diagram is what it is. When I drew the free body diagram, I didn't know which way the forces are pointing, so I just leave it at that. The other equation that I have, sigma Fy equals 0. Anything that points up, I'm going to take positive. Again, start from that star. The first thing I see is AY pointing up, so it's positive. Keep moving to the right, I see a minus 6 kilonewton, and then keep moving towards end of the beam, I see a 4 sine 30 kilonewton, a component of that force, and that's pointing down also, so it's going to be 4 sine 30 equals 0. This will give me AY of 8 kilonewton. And I got this one positive, means the way I drew it on free body diagram is correct. Next, I have to apply my moment equation. Sigma moment about any point you want. Any point you want is valid. But I usually like to take it where more forces are going through. So I'm going to take it at point A, and counterclockwise is going to be positive. This is equal to 0. Start from that star and make your way towards the end of the beam. So the first thing I see, AX and AY, they both go through point A, no moment, but I'm seeing a moment of MA. That's my unknown. Then moving forward, I have a 6 kilonewton at a distance of 1.5 meters, and that 6 kilonewton is trying to rotate the beam this way, which is against my sign, so I'm going to put a negative here. Keep going forward, I see the 4 sine 30, so there's a 4 sine 30 at a distance of, that distance is a little bit tricky. So this one here is 1.5 cosine 30. So it's 1.5 plus 1.5 plus 1.5 cosine 30. And this is also trying to rotate the beam this way. So I'm going to put a negative there. And the next force that I have is 4 cosine 30. The perpendicular distance between point A and line of action of that force, which is right there, and that's going to be 1.5 sine 30 meters. This one, if I pin it at point A, this is also trying to rotate the beam this way, so that's also negative. All of this equals 0. The only unknown I have here is moment about point A, and that is going to be 20.2 kilonewton meters. I got a positive value, so that means whatever I put on my free body diagram was the correct direction that I put it on. Okay, let's look at another one. Find reactions of the supports. Draw free body diagram. All right, step 1. So I'm going to draw a free body diagram of beam AB. So I will remove any support from the beam and just draw the outline. Step 2 is to put active forces. The only active force that I see are those distributed loads. So if you remember from previous lectures, I have to replace that distributed load by equivalent forces. The first thing I'm going to do is divide it into 2 triangles. And remember, the force is area under load, which in this case is half of 3 meters by 400 Newton meters. And that is going to be 600 newtons. Location of it is 1/3 from the base and 2/3 from point A. So it's going to be 2/3 of 3 meters. So that is going to be 2 meters. So I have a force with a magnitude of 600 newtons at a distance of 2 meters. 600 newtons at a distance of 2 meters. Okay. I'll do the same thing for the second triangle. Area under curve, 1/2 of 3 meters by 400 Newton meters, so that is 600. X bar is 1/3 to the base, 1/3 of 3 meters, so that's 1 meters, plus I have another 3 meters right there, so that will equal 4 meters from point A. So I have another 600 newtons at a distance of 4 meters. Okay. So that was just my active forces. Now I have reactive forces. My reactive forces, I have a roller or rocker, same thing, at A, and then I have a pin at point B. I'm going to make X, Y, M. So for point A, I'm going to tilt my X and Y a little bit. You know, I should have said X prime, Y prime. So for point A, it's going to be X prime, Y prime. So let's look at the rocker. We do not look at point B or anywhere else on the beam. Only and only and only we're going to look at point A. Only looking at point A. Is point A able to move in X prime and Y prime, X prime direction? Yes, it is able to. Is it able to move in Y prime direction? It probably can go up but not down, so there's a restriction on it, so it's a no. Can it rotate about point A? Yes. So all I care about is that Y prime, and that is perpendicular to that distance, so I'm going to put a, let's call it normal force at point A. So it's perpendicular to this distance, to this surface, and that is going to, so therefore it's going to be 4, 3, 5, because this one is 4, 3, 5. Okay, so now let's look at point B. For point B, I'm going to just use my normal XY axis. Only and only and only looking at point B. Does this move in X direction? Yes. So I'm going to write yes. Does this, oh, sorry. No, does not. Does this move in Y direction? Nope, because it is fixed. Can it rotate around point B? Yes, it can. That's what pin does. And only care about the no. So I should put a force in X direction and a force in Y direction. So I put BX and BY. So that is my free body diagram. So let me draw it really quick here. I have NA of 3, 4, 5. Should probably copy paste it. And a BX and a BY. Okay. So that is my free body diagram. 2 here, 2 here. Okay. How many unknowns do I have? I have BX, BY, and NA. So I need at least 3 equations. Okay. So let's see. So now I gotta be smart. I gotta start with something, one of those equations that I can find at least one of my unknowns right away. So if you look at point B, both forces, they go through point B. So if I take a moment, I told you that you can take moment about any point you want. It doesn't even have to be on the beam. This way being positive. If I take moment about point B, I don't need to worry about Bx and By. I have only one unknown, and that's NA. So let's look at it. Point B, NA, I have NA. I'm looking for vertical component, so I use the vertical length of that slope triangle, 4/5. And I have NA, this one is 3/5. Okay, and this distance is 6 meters. So if I want to write the moment, the NA 3/5, it goes through point B, so I don't need to worry about it. The only thing I need to consider is N sub A 4/5 multiplied by 6 meters, and this is trying to rotate the beam this way, so it's against my sign, so there's a negative. 600, the first 600 at a distance of 4 meters to point B, and it is trying to rotate the beam with my sign. So that is positive. The next one is the 600 at a distance of 2 meters, the last one. That is also rotating the beam in the same direction. All these equal to 0. I have only one unknown, and I can find my NA to be 750 newtons. Okay, so that's good. So let me write it on the free body diagram. So now I have to write another equation. I can write sigma fx, sigma fy, and just find it easy. But I want to show you that you can use sigma moment about point A and point A now. Doesn't have to be fx and fy. I can use another moment about point A. NA goes through point A. I don't have to worry about it. Let's look at the first. So we're starting from this star. We're moving towards right. The first that I see, the first force that I see is 600 multiplied by distance of 2 meters, and it's trying to rotate it this way against my sign. I'm going to put a negative there. The second force, same way, 600 Newton, 4 meters, rotating this way, and negative right there. The other force, Bx, goes through point A. I don't need to worry about it. And the last force that I have is By at a distance of 6 meters, and it's trying to rotate the beam this way, which is with my sign. I'm going to put a plus next to it. That is my other equation, and I have By equals 600 newtons. The other equation that I can use, because I have only Bx left, I'm going to use sigma f sub x equal to 0. I start from that star again. X component of Na, which is 750 Newton, x component of it is 3/5. It's pointing towards right, so plus 600, 600, both are vertical forces. By vertical forces plus Bx equals 0. This will give me Bx of minus 450 newtons. Again, that minus means when I was drawing free body diagram, I should have drawn Bx the other way. But again, I didn't know, and you don't have to go back and change your free body diagram. Okay. Let's look at another problem. Find the tension in the cable and the horizontal and vertical components of reaction of the pin A. So it tells us that's a pin, so that's good. But if it didn't, simple enough, we can realize that's a pin. The pulley at D is frictionless and the cylinder weighs 80 pounds. Draw the free body diagram. Alright. Step 1, draw the free body diagram of ABC. So that's what I'm going to isolate. I'm not going to include the weight or those ropes or the pulley, anything, because I'm isolating ABC and I need to draw outline of ABC. That's it. Step 1 done. Do not include the ropes, pin, pulley, weight, anything like that. Then put active forces. Active forces are forces that are trying to mess up the equilibrium, which here I see that weight. How much is it? 80 pounds. Now put reactive forces, forces that are trying to hold this beam in place. I like to call that point D. At point D, I see a rope. Ropes are always in tension, meaning going away from the point. I'm going to put T1 or TD. Moving on, at point B, there is another rope, and that is tension at point B. That's also in tension, but it's going straight up. Now we get to point A. It's a pin. If I draw my XY M table, XY M table, I'm going to go a little bit faster here because I've explained it before. Can it move in X direction? No. Y direction? No. Moment? Yes. I only care about the nose. I'm going to put an AX and AY right there. Okay, how many unknowns do I have? AX, AY, TB, TD. It looks like I have 4 unknown. But if you look at this pulley system, if you want, you can draw a free body diagram of oh, I had a point D. Shoot, point D1. There we go. Problem solved. Free body diagram of pulley. Something like this. It's a pin. I like to put an XY and X, dy, dx on a pin all the time. I have TB and I have TD1 going that way. If you want to draw the diagram of pulley, but look at this, it's the same rope. So that means TD and TB are the same. So why don't we just get rid of this B and D and just call them tension. So now it looks better. Now I have 3 unknowns. I have T, AX, and AY. Okay, so again, let's be smart about it. Let's just start with an equation that we can find at least one of those unknowns. If I write my sigma X, I have AX and this component of this T here, which by the way is 1 square root of 5. If I write sigma Fy, again, I have 2 unknowns. So let's just start with the moment. Moment about, let's take point A, because then I don't need to worry about AX or AY. So let's take moment about point A and make it equal to 0. The first force I see is tension at a distance of 5 feet. And it's trying to rotate the beam this way, which is with my sign, so I'll leave it at plus. Next, I have, I'm going to draw it here, T, I have T1 over square root of 5. Vertical component is T2 over square root of 5. Okay, T1 over square root of 5 goes past through point A. So the horizontal component I don't need to worry about. Vertical component, T2 over square root of 5 at a distance of 10 feet this time. And this is still trying to rotate the beam this way, so that is also plus. Moving on towards the end of the beam, I see that 80. And that one is at a distance of 5 plus 5 plus 3, 13 feet. And this time is trying to rotate the beam opposite of my sign. so I'm gonna put a minus there. Sorry, it got kind of messy. I think I can delete some of these stuff here. Okay, better. Equals 0. This will give me a T of 74,583 pounds. 74.6. 3 significant figure. So I know T 74.6, 74.6. I have two unknowns, AX and AY. You know what? This time let's just use sigma fx and sigma fy equals 0. Sigma fx, starting from one side, any force that you see, you have to write it. AX, AY is vertical, T, first T is vertical, second T has a x component, and that x component is 1 over square root of 5, and it's pointing backwards against my sign, so there's going to be a negative. Moving on, the 80 pound is vertical. That's the only I have. And remember, this T is right there, 74.583. This will give you an AX of 33.4 pounds. Okay, the last unknown that I have is sigma fy equals, I can use sigma fy for it. I start from one end of the beam, AX in X, AY pointing up, which is plus. Moving on, I arrive at T, which is 583 pounds. Moving on, I get to the second T, which is 7.583. I gotta use the vertical component of it. And moving on, I get to the 80 pounds, pointing down, so I put a negative next to it, and that is 0. The only unknown here is AY, which is going to be minus 61.3 pounds. I got a minus again. So that means when I drew the free body diagram, I should have drawn AY to the other way. It means the way, so this negative doesn't necessarily mean negative direction of the force. It just means opposite of whatever I drew. Opposite of whatever direction that I drew on there. So let's look at another one with a little bit of different support. So determine the reactions on the bent rod, which is supported by a smooth surface at B and by a collar at A, fixed to the rod, and it's free to slide. This is a little bit of hint. So it tells us which way it is moving and which way it is not moving. So the first step is free body diagram of AB, the rod AB. So that means outline of it, isolate, remove every support. If you want to really get artistic, at point A you can draw the collar, but doesn't really matter. Step 2 is put the active loading. See, I didn't use forces this time, and you see why, because I have a force but I also have a moment. This is the first problem, that we have an existing moment. Why is that moment there? It's a free moment. It's a couple moment. You can move it, put it anywhere you want. It's a free vector. But remember, for problems like this, it's always better to keep it where it is. Don't mess up what the problem gives you. Point B is a smooth surface. If my x prime, y prime are this way, does this move in x direction? Yes. Does this move in y direction? No. Can it rotate? Yes. So I need to put one force in y direction, and it needs to be perpendicular to that surface. So I have a normal force of NB. That a slope triangle is 5, 12, 13. So a slope triangle, and this one is opposite, is 12, 5, 13. And then I get to point A. So again, for point A, I'm going to make that little table for myself. here. So something like this. I put an X, or sorry, Y and X. Does this move in this direction? Yes. It says it's free to slide. Does this move in this direction, perpendicular to the rod? No. So that's what I care about. I'm going to put perpendicular to that rod direction. So that one is 4, 3, 5. This is perpendicular, so this is going to be 4, 3, 5. Does this rotate? I don't think so. That rod can only slide, so there's no rotation. So I need to put also a moment as a reaction towards end of it. Okay, so let's see, how many unknowns do I have? M sub A, this one I didn't give it a name. Let's call it normal force at A and normal force at B. So I have 3 unknowns. Again, I have to, if you let me draw it really quick here. MA, perpendicular NA with 3, 4, 5, 200 pound feet, and normal at B with 12, 5, 13. Don't forget the 100 pounds. There we go. Okay. I have 3 unknowns and I have to write equations. So any of the equations I use, I'm gonna end up with 2 unknowns in them. Sigma fx, sigma phi, or moment. So it really doesn't matter which one to start. So let's just start with writing a moment about point A, make it equal to 0. So starting from point A, NA goes through A, doesn't matter. MA exists and it's with my sign, so that's plus. Moving on, I got 100 pounds multiplied by the distance, perpendicular distance between point A and line of action of that force, which is 3 feet, and it's trying to rotate the beam this way about point A, and that's against my sign, so that's minus. Yeah, that is minus. And then I have 200 pound feet that is also against my sign. And I have NB. Okay, so for NB, I have to find the components. There's no way around it. So this one is going to be NB 12 over 13. And then I have another force that is NB, and this one is, oh sorry, this one is 5 over 13, and this one is 12 over 13. Okay, now I'm taking a moment about point A. So let's just start with NB 12 over 13. The perpendicular distance between point A and line of action of this force is the whole length of this beam, 6 feet. Which way is trying to rotate it? It's trying to rotate it this way, which is with my sign, so I'm going to put plus. The next one, I'm going to go next line. NB 5 over 13, the horizontal force. Perpendicular distance between point A and line of action of this force. This is the distance I'm looking for, which is 2 feet. And which way it's trying to go? This is trying to go this way around point A, and that is against my sign. So there should be a negative and equal to 0. So let me delete this again. Sometimes I get too excited and draw. My rotation is too big. So if you would do this, I have NB and MA. I can't do it. So I got to write another equation. Let's write sigma Fx, summation of forces in x direction, be 0. So I start from one side. I have NA, the x component of it, is going to be 4 over 5. And it's pointing towards right, so that's plus. I keep going, 100, pointing down. I go till I reach NB, which I'm looking for x component of it. NB 5 over 13 equals 0. Then I get to sigma Fy equals 0. Starting again from point A, I have to use the vertical component of NA, which is 3 over 5, pointing up, so it's plus. And going all the way, now I'm looking at vertical component of NB. 12 over 13, pointing up, but I also have that 100-pound existing force on there. So as you can see, I have 3 equations and 3 unknowns. So if you do the math and you do the 3 equations, 3 unknown, you are going to get 3 values for the 3 unknowns. So I'm going to give you the answer if you want to check them. NA is going to be 339.7. NAB and sub B is going to be 82.5. And M sub A is going to be 106 pound-feet. Okay, so I did 3 equations, 3 unknown, and I got these final answers. Okay, let's look at another example. A cantilever beam, which means a beam that has fixed support on one side, or just support on one side, free on the other. Okay, so fixed or any kind of support on one side, fixed on the other. Calculate support reactions at point O. Okay, step 1, free body diagram of the beam. So I'm going to remove supports on anything, draw the outline. Then put active forces, or active loading, I should say, 3 kilonewton. I have a moment, which I told you to keep it where it is, 1.4 kilonewton. And now I point O. So I have fixed support at point O. If I draw the table really quick, does it move in X? No. Does it move in Y? No. Can it rotate about point O? No. So I got 3 no's. That means 3 type of loading. I'm going to put dx, dy, m about point O. This is my free body diagram. How many unknowns do I have? dx, dy, mo. Okay. So let's see. If I write fx or fy, I should be able to find dx or dy. So it doesn't matter which one I start. Let's start with summation of forces in y direction. Anything that points up, I'm going to put a plus next to it. Start from one side. dy is my first unknown. dx, mo, I don't care. It's pointing up, so it's going to be plus. Moving on, I arrive at 1.4 kilonewton pointing up, so that's also plus. Moving on, 15 is a moment. Next one is 3 kilonewton. So I gotta use the vertical component of it. The angle is given as 30, so I'm gonna use 3 kilonewton cosine 30. That one is pointing down, so I'm gonna put minus. And I get dy. Why did I draw D? This is point O. Sorry about that. OY. So I'm going to get OY of 1.198, or if I want to use 3 sig figures, it's 1.2 kilonewton for point OY. Okay. The other one, summation of forces in x direction being 0. I start from one side, OX, OY, M, I don't care, 1.4 is vertical, 15 is a moment. I go all the way till I reach the 3 sine 30. the x component, and it's pointing against my sine, so I'm going to put minus 3 sine 30. This will give me an OX of 1.5 kilonewtons. Okay. I have one last moment to take care of, and I'm going to take moment. It's usually better to take your moment about your support. Usually, it really doesn't matter where you take it. If I take the moment about point O being 0, okay, start from the end of the beam. OX and OY, they go through point O. We don't care about them. MO, on the other hand, exists right there, and it's with my sign, so it's a plus. Moving on to 1.4 kilonewton is located at a distance of 1.2 meters to point O, and is trying to rotate the beam this way, which is with my sign, so I'm going to put a plus next to it. Moving on, I see a 15 kilonewton meters. That's a moment. I have to include it in my summation of moments. And that is rotating with my sign that I have here. So that's also plus. Moving on, I have two forces at the end. A 3 kilonewton cosine 30 and a 3 kilonewton sine 30. The sine 30 goes right through point O. So I don't care about that one either. The only one I care about is 3 kilonewtons cosine 30 at a distance of 1.2 plus 1.8 plus 1.8, which is 4.8 meters. It's pointing down, so it's trying to rotate the beam this way around point O, and that's against my sign, so I have to put a negative right there. The only unknown here in this equation is my moment about point O, which I will get 1.21 kilonewton meter. I got a negative. That means against the way I drew it. It goes against the way I drew on my FBD. All right, let's look at another problem, which is very similar to the one that we just did, but it has an important point that I want to mention. So find the reaction at point A and the tension in chord BC. If F is this much, moment is this much, free body diagram is required, neglect the thickness of the beam. Okay. As always, we start with free body diagram. Very, very important point is to figure out what is it that you're drawing free body diagram. Beam AB. And only beam AB. So that means you do not include that point C or the rope or anything like that. So let me draw the free body diagram. So the outline of point AB. Step 2 is active forces, or active loading, I should say, to be 100% correct. I have a moment of 150 kilonewton meters. I have a force of 26 kilonewtons at 12, 5, 13. I have a force of 40 kilonewtons. These are my active forces. Now I'm going to go look at reactive forces. I have a tension that is supporting the beam at the end, 3, 4, 5. And I have a pin. So, and this is an important point about this problem. It's very important to draw the active loading first, the existing moments first. This one is active. Because when you want to look at the pin, if you remember, doesn't move in X, doesn't move in Y. Yes, it can rotate about, why did I write Z? It can rotate about point A. It can, and we only care about the nose. So usually when we want to draw the reactions at point A, we only put an AX and an AY and not a moment. The reason we have a moment here is because there's an existing moment. So that was the important point about this problem. Otherwise, the rest is very straightforward. So I'm going to just do it a little bit quicker for those of you who are interested. Otherwise, I've explained everything repeatedly in previous problems. So starting from the end, the only thing I have is moment. Then moving on, I have the vertical component of 2612 over 13 kilonewton at a distance of 2 meters. Trying to rotate my beam this way, so I'm going to put negative next to it. Moving on, I have a 40 kilonewton at a distance of 2 plus 4, 6 meters. It's trying to rotate the beam the same way, so it's negative. And then I have a tension, which I only care about the vertical component because the x component of it goes through point A. So it's going to be T. The vertical component is 3 over 5 at a distance of, that one is also 6 meters. And that one is rotating my beam this way. So that's a plus. And there we go. The only unknown here is T, which I'm going to get 38.3 kilonewton. Reaction tension. So we find tension. We need to find reactions, which is AX and AY. Once we know that, very simple. We got to use summation of forces in X direction. Starting from one side, AX pointing towards right is a plus. Moving on, I have a 26.5 over 13. The X component of that force pointing towards left, so that's negative. Moving on, 40 is a straight down, and tension that has a 4 over 5 component. And it's plus, and T, I just found it to be 38.3. The only unknown here is AX, and I'm going to find AX to be 20.26 kilonewton, or 20.3 if I want to go with 3 significant figures. And the last equation that I have left and I'm going to use is use sigma Fy equals 0. Anything that is in vertical direction right off the bat starts with AY. Moving on, the vertical component 12 over 13 of this force pointing down, so that's minus. Get to the 40, that's pointing down, so that's minus. Get to the T 3 over 5, that's pointing up. There we go. Again, I have the T as 38.3. The only unknown is AY. So I'm going through these a little bit quicker because I've explained them in previous problems. Find the reaction. That's a little sneaky little point there, because it asks to find the reaction at point A. Okay, so I have an AY and AX, so you know how to find the resultant force. So A is going to be 41.2, 20.26. So this will result in 45.7. So if I want to just replace it by one force and not components, just a little practice and kind of refresher of what we've had in previous chapters. Looking at the last problem I have, I already did one with distributed load. Let's do another one. Part A, show the distributed loading on this beam as a single equivalent force and find its location from point A. Okay, now we're going way back to previous chapters. So the first thing to doing that, so the first part doesn't care about free body diagram. There's no reactions. It only want to replace that force with a single distributed load at a distance. So the first thing I do, I have to divide this area into areas that I'm comfortable finding and working with. So I'm going to make a triangle sitting on top of a rectangle. This rectangle is going to have an F1. That triangle is going to have an F2. All I have to do is find this F1, which is area under this rectangle, which is 2 kilonewtons per meter with the length of 6 meters. So it's going to be 6 meters, 2 kilonewton per meters, and that is going to be 12 kilonewton. The x bar of it is center of that area, which is half of the length, so it's 1/2 of 6 meters is 3 meters from A. Okay, found F1. F2, let me see, this whole length is 5, so this is 3 and this is 2. Area of the triangle is going to be 1/2 of the whole length, 6 meters, multiplied by the base, 3 kilonewton per meter. So that is going to be 9 kilonewtons. The distance of it from point A is, this is 2/3 of the length. So it's going to be 2/3 of 6 meters, which is going to be 4 meters from A. Okay. So again, remember this, we are not doing free body diagram. We are not doing the support yet. So this is not a free body diagram that I'm trying to do. Not a free body diagram. Point B. So far, I have F1 of 12 at a distance of 3. I have another force of 9 at a distance of 4 meters. So I should have put them closer with each other, but it's not to a scale. Why did I bring that force down, F2? Because remember, force is a sliding vector. As long as I'm sliding it on its line of action, I can do that. I can totally bring it down and put it right on the beam. The problem happens when you start moving it and it's not on its line of action. So the next step that I do, remember, the goal is to have one force at a distance d. That's what the problem is asking us. So far I have 2 forces and each are at a distance point A. So what I'm gonna do, find these two, remember from previous lectures, summation of forces. So my FR is going to be 12 plus 9, or if you want to take up as your plus sign, then both of these are going to be negative, but you get what I'm trying to do here. So my FR is going to be 21 kilonewtons. My MR is going to be summation of those forces, which is going to be 12 kilonewton multiplied by 3 meters plus 9 kilonewton multiplied by 4 meters, which is going to be, I don't have the final number for it, so it's 3672 kilonewton meters. And if you remember, that distance is, so far what I have is a beam like this. Sorry, it's getting kind of crazy. I have a force of FR equal 21 kilonewton and a moment of 72 kilonewton meter. I want to move the FR so I get rid of that moment. And we've discussed this in detail. So if you have questions, you have to go to previous lectures to figure out what the procedure is. Going kind of fast through this. And I get 72 over 21, and that will, oh, sorry, kilonewtons. These two cancel each other out. All I have left is 3 meters. Okay, that was part A. Part B says find support reactions. All right, so let me draw this really quick. So I have a 21 kilonewton at a distance of 3.43. I have a pin, and I just like to draw it like this, a roller at point B. I don't care about this anymore. Remember, I simplified it to this. I did all that work, so now I'm going to use it. So now my problem just starts. I have a beam with a force on it. It asks us to find support reactions. Free body diagram. Now this is free body diagram of the beam. Outline of the beam. Remove the supports and everything. Put active forces on there. 21, 3.43. And reactive forces. I have a pin. I have a roller. X, Y, moment. Pin, no in X, no in Y, yes to moment. Roller, yes to X, no to Y, yes to moment. These are the only one I care about. So I'm going to put in AY, AX, and a BY at point B. So this is my free body diagram for the beam. So this is kind of straightforward based on what we've discussed. Sigma forces in X direction being 0. I start from one side. The only force I have is AX. There's nothing else. So that means this force should be 0. But I still need to have it on my free body diagram. The other one, let's write sigma forces in Y direction being 0. I start from one side, plus AY, moving on, minus 21, plus BY equals 0. I can't do this. Two unknowns. So let's write a moment. Let's write moment about point A, because there are two forces that going through it. So moving on, 21 multiplied by 343 meters kilonewtons, and that is negative. That goes against my sign. And moving on to BY at a distance of 4 meters. It's trying to rotate the beam this way, which is with my sign, equals 0. This will give me a BY of 18 kilonewton. Okay, now I can go back here and find this. So if I put BY equal to 18 kilonewton, I'm going to get AY of 3 kilonewtons. Thank you. That's all I had for this lecture.